You're watching a Channel 98 NBISD TV production.
Oh, hey, hi there. I'm Mr. Corpy. I'm just working one of my math problems here, one of my favorite things to do. If you've tuned into this program because you like math, then great, stick around. If you happen just to stumble across the show, then I invite you to stay a little while, relive some mathematical memories, because the name of this show is Deja Vu. It's Algebra 2. Aha! It's whole. It's seventh. It makes 19. This brief and strange-sounding sentence is an ancient Egyptian's 3,600-year-old attempt at making sense of the world around him in order to discover an unknown quantity. His goal? To collect and arrange his known given quantities in a sequence so that through a systematic set of ordered procedures, he could arrive at the correct numerical value. Found on the Rhine Papyrus, it poses one of the earliest problems solved by man's algebraically. In ancient times, there was no algebraic notation and hence no absolute general method of solution. Instead, equations had to be written out in words and they were presented rhetorically or verbally. The ancient Egyptians' method for solving them was called regula falsi, or the rule of false. It was kind of a systematic guess, check, and revise method. It was very effective, but not entirely efficient. The word aha, though it sounds like an exclamation of discovery, not unlike Archimedes' Eureka, actually translates to the word heap. It was used to represent the unknown quantity in the problem. Now today with our fully developed algebraic notation, the expression would read as follows. So they used the word aha to denote the heap. So it read, aha, it's whole, so there's a whole aha, we call it an X today. It's seventh, so that's a seventh of aha, so X sevenths. It makes, that is our equal sign, 19. So that's what the equation would look like today. And now we have very systematic methods for solving this. And the way to do that is to combine our like terms. And we're going to save the actual calculations for later on in the show. Some of y'all may be at home and you may want to try to do this. And if you think you have the correct process, I'll tell you what the answer is here in just a minute so you can check. Additionally, with our systematic methods for solution, this linear equation can easily be manipulated to discover the unknown quantity, 16.625. Now, Algebra 2 is designed as a sequel to Basic Algebra 1. This show will be an extension of the Algebra 1 show, all about algebra, which hopefully many of you are fans of, with topics including things that you're familiar with, like polynomials, factoring, rational expressions, exponents, radicals, and quadratic equations. That's all familiar ground, so deja vu on that. But we'll be looking at different types of functions that are entirely brand spanking new. Functions like exponential, logarithmic, radical dude functions, and rational functions. We'll also venture bravely into the study of basic trigonometry, which is an intro to pre-calculus. We'll be looking at complex numbers, identities, binomial expansion, and matrices, and everyone's favorite, determinants. Now, throughout the year, we'll make considerable use of the graphing calculator. I will be using specifically the TI-83, and you'll be able to follow at home the keystrokes that you need to do on your calculator at home to do the calculations I'll be doing on the show. So in watching this show, you will build upon the skills that you acquired in your Algebra 1 and Geometry classes with the goal of developing further competencies to enable you to take more advanced math classes. Classes like pre-calculus, calculus, statistics, or even Algebra 3 at the high school level, or even eventually enroll in a college-level algebra course. In actively working along with me at home, you'll further develop your organizational and study skills that support the acquisition of new algebraic skills. Finally, you're going to develop self-confidence in yourself and in your math abilities, alleviating your feelings of math anxiety, and hopefully coming to grips with just how fun math can be. All right, so what is algebra? I know you're asking it. Well, algebra may be divided into two separate branches, what we call classical algebra, which is basically equation solving or find the unknown number problems. And then recently there's a movement called abstract or modern algebra, which is the study of groups, rings, and fields, etc. Now, classical algebra has been developed over a period of about 4,000 years. Abstract or modern algebra, however, has only appeared in about the last 200 years. We are going to focus primarily in this show, if not exclusively, on the first variety, the classical algebra, because that's what you're going to encounter in a typical high school algebra or algebra 2 class. Now, the development of algebra through the 4,000 years of classical algebra has fallen under the following major influences, and I'm going to talk about these today. The first is the Egyptian algebra, which I already mentioned, which was found in the Rhind Papyrus. Then we have the Babylonians' contribution, so we have Babylonian algebra. We got the Greek geometric algebra. And then we have the Hindu algebra, moving on to the Arabic algebra, and finally the European algebra since 1500, Renaissance era and beyond. And then we move into the modern algebra, pretty much what's being studied today, new stuff that's being studied and discovered. Now, since algebra grew out of numbers and number systems and the operations that we do on those number systems, specifically arithmetic, the recognition of new number sets and new number systems, such as irrationals, zero, negative numbers, and complex numbers, is an important part of algebra's history. And it will be an important part of this Algebra 2 course as well. The development of the algebraic notation that you're going to see throughout the year progressed through 3 stages in the history of algebra. The first was the rhetorical, or the verbal stage, which was indicative of what I read at the beginning of the show. Then we had the syncopated stage, which is kind of a combination of verbal and symbolic. Abbreviated words were used and some symbols, but it was kind of a verbal abbreviated word stage. And then we transition into the pure symbolic stage of algebra with which we are all familiar, or hopefully with which we're all familiar. It's the one that takes place in our algebra classroom and what we're going to be talking about on this show. So, we've already mentioned the Egyptians' contributions. Their form was called the rhetorical form, and the aha problem at the beginning of the show was what the ancient Egyptians were doing. So, let's move on to the Babylonians now. Babylonian algebra. I'm sure it's on everybody's mind, right? Well, the Babylonians did develop a style of writing, so we've been able to discover their contributions as they were preserved in a style of writing called cuneiform, which was written on clay tablets. So the mathematics of the Babylonian period took place around 1800 to 1600 BC, and it was more advanced than their counterparts in Egypt. Their math utilized what's called a sexagesimal base number system. Sexagesimal means base 60. And the base 60 number system really led to some highly developed algebra. Our custom today of dividing a circle up into 360 degrees, or 60 seconds in a minute and 60 minutes in an hour, are really cultural artifacts that have been passed down to us from the ancient Babylonians. The Babylonians were also able to solve quadratic equations, which we'll study later on in the year, degree 2, and they worked with systems of equations. That's more than one equation with more than one unknown, more than one variable. Now, there was some use of symbols, very limited use of symbols, but not much. And like the Egyptians, their algebra was essentially rhetorical or spoken. And they only accepted positive rational, which means fractional, solutions to all their equations. Which means they rejected negative numbers, they rejected irrational solutions, and they rejected zero. Zero has a big history. So, past the Babylonian era, we move nicely into what's called the Greek geometric period of algebra. Now, the Greeks, they also rejected irrational numbers, but they also insisted on representing quantities as geometric magnitudes. They really were all about geometry. They focused more on the form of numbers, such as triangular and square numbers, which I'll show you right here. So again, the Greeks' fascination with geometry led them to think of numbers in terms of shape. So they had their triangular numbers. And what is a triangular number? Well, if you think of forming a triangle with 3 dots, that would be the number 3. 1, 2, 3 dots. So 3 is considered a triangular number. What would the next triangular number be? Well, to those 3 dots, to make a triangle, we would have to add 1 on the diagonal, 1 down here on the bottom, and there's another one. And that would give us our next triangular number, which is 6. So notice the geometric form, and that's what they were interested in. The square numbers, we still kind of use square numbers today because squaring is an operation that we'll encounter in algebra. So a square number would be something like this. You make a square with your 4 dots, and that would be 4. Now square numbers, again, the geometry of them is fascinating. You can actually learn algebra by using squares. And I know on the All About Algebra show, you actually use algebra tiles. So this would be a square number. The next square number would be, to build on this square, we would have to add some numbers down the side. And so the next square number would be 9. And then the one after that would be 16. And these are all our perfect squares that we know from algebra. So we call this 2 squared. We call this 3 squared. So there is kind of a residual, something that we adopted from the geometry of the algebra by the Greeks. Now, although this period ultimately gave us the Pythagorean theorem and had great mathematicians like Archimedes, arguably one of the greatest of all times, one of the top 3, of course, and many, many more great ideas mathematically, the geometric approach to algebra was really of little practical value, and it actually slowed the development of the symbolic algorithmic algebra that we are studying today for several centuries. Okay? So they were really more of philosophy and geometry. We move now to another era, a later Greek mathematician by the name of Diophantus. Diophantus, although he was Greek, came along much later, around 250 AD. And Diophantus is regarded as one of the first individuals to move from a geometrical algebra to a treatment of algebra which did not depend upon geometry. And for that, he is generally regarded as the father of algebra. So your algebra dad is Diophantus. All right, you got it? Now, although the rhetorical/verbal style was still in use, he introduced the syncopated style of writing equations, where words were abbreviated and some symbols were used. It was a combination of verbal and symbolic. In his landmark book called Arithmetica, he gives a treatment of what he calls indeterminate equations. And all that is usually 2 or more equations in several variables, which means there are many, many unknowns, which also means they have infinite number of rational or fractional solutions. Now, such equations today are called Diophantine equations. And although the use of symbols and abbreviations was a major leap from the rhetorical style, the verbal style, Diophantus did not develop general methods for solving any of his equations, okay, like we have today. In fact, each of the 189 problems in his book, Arithmetica, is solved by a different, unique method. Now, he too only accepted positive rational roots, which means he rejected irrational, he rejected 0, and of course he rejected negative numbers, like many of his predecessors. They just didn't acknowledge them as real solutions. That's a lot of information to take in one sitting. Why don't you go take a break and come right back to Deja Vu. It's Algebra 2. I'll be here waiting for you.
Yesterday, my friends told me to smoke some weed, and I did. Then today, they said I should try to outrun Tick-Tick, the little lumberyard dog. And I don't think I can. I'm an idiot. I'm doing stupid stuff, and that ain't me.
Live above the influence. Above them, above weed.
Hey, welcome back to Deja Vu. It's Algebra 2. I'm Kevin Corpy. I want to let y'all know that anything that I'm going to be doing on the show, including today's fabulous historical lesson on algebra, is available for you to download from our district website. All you got to do is hop on to www.newbraunfels.txed.net, and it'll be all right there for you. Download as many copies as you want. Work the problems as many times as you want. All right. Okay, so where can you go after the father of algebra, Diophantus? Well, we move into a period of development called Hindu algebra. Hindu algebra, they basically took all the contributions that the Greek made in the history of mathematics, and they took it and ran with it, essentially. Okay? Now, although the Hindu civilization dates back to at least 2000 BC, their record in mathematics dates from about 800 BC. But really, it only became significant after they were influenced by the achievements of the geometric Greeks in algebra. Now, most Hindu mathematics was motivated by practical problems based in astronomy and astrology. They did, however, use a base 10 number system like what we use today, and they were the first to use a positional notation system, which is kind of like a number line thing, a well-ordered number line where we can relate two numbers as being equal, less than, or greater than. And this system, base 10 positional notation, was pretty much standard now because of the Hindus by about 600 AD. The Hindus treated 0 as a number. Yes, they acknowledged 0, and they even discussed operations involving 0. They were not afraid of 0. They also introduced negative numbers as representation of debt. So they were the first to use 0, the first to use negative numbers. The first known use of a negative number was by a guy named Brahmagupta. Fun to say, Brahmagupta, around 628 AD. The Hindus then recognized also that a positive number, such as 4, has two square roots, positive and negative. Remember, they recognized negative numbers. They also developed, they just went on and on. They also developed correct procedures for operating with irrational numbers. So look at this. Everyone before them rejected irrational, they rejected 0, they rejected negatives. The Hindus embraced all three of those types of numbers and number sets. Now, what did they do in terms of algebra? Well, they made progress in algebra as well as the arithmetic. They developed some symbolism which, although it wasn't real extensive, was enough to classify Hindu algebra as almost symbolic. They were really, really close to what we're doing in the classroom today. It was certainly, however, more sophisticated than the syncopated style of Diophantus. So, really, really cutting-edge Hindus there. So now that we have the Hindus, where can we go? We're really crescendoing up here in terms of algebra. Who would be the next great group to come along and take their ideas and run with them? Well, it is the Arabs, actually. Okay, so which brings us to our next period of Arabic algebra. Now, this is kind of interesting here. While much of Europe was in the Dark Ages, the Arabs were in their Golden Age, and they preserved all the Greek learning, and they flourished in the study of the arts and sciences. In fact, Baghdad at this time became a mecca for intellectual and artistic pursuits. And these Muslims then, they took over and they improved the Hindu number symbols and the idea of the positional notation. The numerals, which they developed, which are called the Hindu-Arabic system, or just the Arabic system of numeration, and the algorithms, the processes for operating with them, were all transmitted to Europe around 1200 AD, and they are still in use throughout the world today. It's what we use, the Arabic number system. Now, in algebra, what did the Arabs do? Well, first of all, they contributed the name. Yes, the name algebra. It comes from the title of an Arab text, which is called Hisab Algebra wal Muqabala. Did you catch that? Hisab Algebra wal Muqabala. Did you hear a word in there? Algebra. It was written about 830 AD by the astronomer, by the mathematician, Muhammad ibn Musa al-Khwarizm. Okay, got that? Now, this book was a landmark book in itself. It was a systematic expose of the basic theory of equations with both examples and proofs. And it's interesting that our word algorithm, which we actually use to define a systematic process, comes from a corruption of the author's name, al-Khwarizm. Okay, just like algebra comes from the book Algebra, algorithm comes from the author's name. So algebra is really about algorithmically solving equations. And it all comes from this one guy, this one book. Okay? So while the ancient civilizations wrote out algebraic expressions verbally using only abbreviations like the syncopated style, by medieval times the Islamic mathematicians were able to talk about arbitrarily high powers of the unknown. X to the 5th, x to the 10th, x to the nth power, arbitrarily high. And they worked out basic algebra of polynomials. These are multi-termed animals that have multiple x's to different powers in them. And they were able to work out solutions to these, but when they did it, they didn't quite yet use the modern, purely symbolic notation. So it was still a syncopated style. And so we have not yet progressed quite where we are today. Which brings us to European algebra after 1500. So all these great ideas from the Arabic or Muslim Golden Age trickled into Europe during their Dark Ages, and it led to one of the most famous periods in all of history, European history, and that's the period of the Renaissance. So European algebra after 1500 was something very special. This is where things really got going in terms of symbolic algebra. At the beginning of this period, 0 now has been accepted as a number, and irrational numbers were used freely, although people had to admit that they still worried about whether in fact they were really numbers or not. Negative numbers were known. People knew about the numbers. Remember, the Hindus used them, but they didn't really fully accept them. Not quite sure what a negative number meant. Complex numbers, yeah, that was still years away. People still didn't imagine complex numbers, which is basically the imaginary numbers, or the imaginary numbers are part of the complex number system. So full acceptance of all the components of our familiar number system that we're going to be using in class and on the show did not really come until about the 19th century. Now, algebra in 1500 was still largely rhetorical. Renaissance mathematics was to be characterized by the rise of algebra, among many other things. In the 16th century, the main focus was on solving polynomial equations. During this time, there were great advances in technique, namely general solutions to the cubic equations. That's degree 3 equations. There were also, at this time, many important improvements in symbolism, which made possible now a science of algebra as opposed to the collection of isolated techniques or a bag of tricks, which is what a lot of people, unfortunately, think all algebra is. But that was the trademark or the content of algebra up to that point. So who can blame them, right? Well, publication of many of these results in 1545 in a book called the Ars Magna by an Italian Renaissance mathematician, get this, you're going to love it, physician, astrologer, and gambler. Yeah, a lot of people back then gambled, and a lot of the math, especially probability math, generated out of gambling. This guy's name was Girolamo Cardano, or sometimes he's called the Great Cardan. Okay? It's often taken, this book, to mark the beginning of the modern period of classical algebra. Remember, classical is not yet the abstract algebra. Now, the landmark advance in symbolism from the syncopated style was made by a French mathematician named François Viète. François Viète. He was about 1540 to 1603 is when he lived. And he actually used individual letters, single variables, to represent known constants. He called those parameters. Now, this advance really freed algebra from the consideration of particular equations, and so it allowed a great increase in the generality of solutions. Now, Viète's algebra, however, was still considered syncopated. It wasn't entirely symbolic. Symbolic algebra did not reach its full maturity until the publication of French mathematician, philosopher, and great guy, all-around great guy. He was also a metaphysicist, too. His name, one of my favorite mathematicians, René Descartes. And his book, Les Géométries, in 1637, gave us the full symbolic mathematics, or symbolic algebra, that we were looking for. And it also did one better than that. It gave us the wonderfully fruitful marriage of algebra, symbolic algebra, and geometry of the ancient Greeks in what today we call analytic geometry. And analytic geometry is basically now what students study in part in a pre-calculus course. So we have René Descartes to thank for that. Now, work did continue throughout the 18th century on the theory of equations, but it wasn't until the turn of the century, 1799, when a proof was published by a then 22-year-old German mathematician who was writing his PhD in mathematics, and his name, Carl Friedrich Gauss. He's considered one of the big three mathematicians, right alongside Archimedes and Newton. And what he did is he showed that every polynomial equation has at least one root in the complex plane. Now, that is a very important idea. Complex numbers, it brought them onto the scene. We're talking about a complex plane now, which is different from René Descartes' Cartesian plane. And he's talking about a guarantee that a polynomial equation will have one solution in the complex plane. This was so important, it became eventually known as the fundamental theorem of algebra, which means that pretty much all the ideas of Algebra 1 and 2 are basically consequences of this great theorem. And Gauss loved this theorem so much that he went on to prove it 3 different ways on 3 different occasions after the first in the course of his lifetime. The last time being almost 50 years after he proved it for the first time at the age of 22. He was a very gifted mathematician. Now by this time, algebra had entered its modern phase, which means we're out of the classical phase. Solving polynomial equations now, all the mystique was taken out of it, and we had developed a very systematic way to solve these types of equations. So instead, the attention now shifted from solving polynomial equations to studying the structure, the overall structure of the abstract mathematical systems, the systems themselves whose axioms and theorems were based on the behavior of mathematical objects that were encountered when these mathematicians were studying polynomial equations, such as the complex numbers and the complex number systems themselves. And that's what most of the new study today in algebra is. So if you hear a college professor talking about algebra, he's talking about abstract algebra, which is the study of algebraic structures, groups, rings, fields, and all that stuff. Now in this year, we're going to retrace the historical development of this great algebra branch of mathematics. We're going to be learning the symbols. We're going to be applying the proven systematic methods. We're going to be finding the roots of these polynomial equations. And we're going to be learning all the skills required to do this that have been developed and discovered by real people who devoted their entire lives to this subject. And all the fruits of their labor are now what fill the content of your textbook. And it's worth revisiting that. So I hope, as this year goes on, you'll join me each week, and you'll venture into the great unknown in search of the mysterious X. And as you do, you'll hopefully get more comfortable, and you'll develop a distinct sense of familiarity with the syntax, with the symbols, and with the structure involved. In essence, you will feel a sense of deja vu for Algebra 2. Until next time, I'm Kevin Corpy, reminding you to do your homework.